All right, so today is a special day because today it's the 8th Memorial Lecture honoring the life of Professor Dimitri Kececioglu. So the Dr. Dimitri B. Kececioglu Lecture is actually now an endowed lecture thanks to the generous financial support of the Kececioglu family. In fact, Dr. Kececioglu's daughter, Zoe Drylos, is actually an alumnus from our department. And in 2024, she was alumnus of the year from the College of Engineering and also alumnus of the year for the College of Medicine. Okay. So for the graduate students here who do not know who Dr. Kececioglu was, so he was a towering figure in the world of engineering reliability. Okay. In fact, he has 8 books on the topics of reliability. He has led the Reliability Institute here at the U of A for more than 40 years. Okay. And he's been extremely active in workforce development in the field of reliability. In fact, he's developed a graduate program in reliability here in the AME department, and he has organized many workshops. In fact, there's a few programs in reliability in the US who basically used the program that was here in the AME department as a blueprint for their program. And many of his students have attained high positions in the field of reliability in large companies. And in fact, one of his students created a company called ReliaSoft, which is a major player in the field of reliability. So originally, so this first lecture started in 2015, and the main focus was on engineering reliability. And as we went, actually the topic of this lecture have morphed into not only reliability, but they've morphed to include risk assessment and uncertainty quantification. Okay. So to honor Dr. Kececioglu's achievements, we have the immense pleasure to receive Dr. Wei Chen from Northwestern University. And we're delighted that Dr. Chen accepted the invitation. So let me tell you a few things about Dr. Chen. She's a Wilson Cook Professor of Engineering Design and Chair of the Department of Mechanical Engineering at Northwestern University. She's the Director of the Integrated Design Automation Lab. And she's an extremely well-known figure in the area of not only engineering design, but also MDO, which stands for Multidisciplinary Design Optimization. Okay. Her research interests include material design, like we're going to see today, in particular with integration of machine learning and uncertainty quantification techniques. And she serves as a design thrust lead for newly funded NSF Engineering Center on hybrid autonomous manufacturing. She's received many awards and titles. You can see that in her biography, but I'd like to just highlight a few. She's an elected member of the National Academy of Engineering, NAE, and the American Academy of Arts and Science. She served as the editor-in-chief of the Journal of Mechanical, ASME Journal of Mechanical Design, and she was the chair of the ASME Design Engineering Division, DED. And she was the president of the Society of Structural and Multidisciplinary Optimization. Okay. She was the recipient in 2022 of the Engineering Science Medal from the Society of Engineering Science. And finally, in 2015, she received the ASME Design Automation Award. So without further ado, Dr. Chen.
Thank you very much. I really like to thank everyone, including those people online, joining this lecture, listening to the story of Professor Dr. Dimitri. I feel really extremely honored to be invited. So thank you very much for SAMI and also for the department. So what I will share with you today is a research I've been working on during the past decade using data-driven computational methods for engineering, for designing engineering material systems. It's really a collaboration, a lot of people who contribute to this. I listed here my students as well as faculty, collaborator, cross over many different institutions. Wearing my department chairs hat, I want to also say a few words about my department. just like I don't travel too much to here, I also wondering, how many of you have traveled to Chicago? How many of you actually be there? And your department chair, of course, is moved from Chicago, maybe 1/3. So we're very close to Chicago in a neighborhood city called Evanston. But you may wonder why it's called Northwestern University, right? That's because when it was first founded, that's 18-something years, at that time, the US, Chicago is actually at the northwest side. So there's no Arizona and California at that time yet. So that's the reason why it's called Northwestern University, because it was at the edge. And this is the building where all the engineering department were in one big building, okay, many engineering disciplines. So it's not a big school. So my department has actually 3 major disciplines. So if I think about the difference between this department and our department, first you have Aerospace program, which is a big program. Secondary, we don't have a critical mass in this fluids and the heat transfer area. It's kind of lumped into mechanics, so it's part of the mechanics and materials. We do have lots of people in there. And I'm in the design manufacturing, and we have robotics and the biosystem group. So we're working on, we call the 7 cross-cutting area, including like AI design, advanced manufacturing, nano, microengineering, and so on. We have a little bit slightly bigger department, maybe 31 in terms of faculty number, 31 core faculty, and 10 of them are jointly appointed with other departments. So it's very much, Northwestern has its culture that enabling, encouraging collaboration. One thing I'm very proud of my department is a really high scholarship standing. We currently have 6 NAE members. Actually, I think 5 of them, all 6 of them were elected in the past 7 years, because we have a previous generation of NAE either retired or actually some of them passed away in the pandemic area. Also, NNS as NAI stands for National Academy of Innovation. So we also have some people who are very great innovators and 8 journal editors-in-chief. You may be wondering about the ranking. We like to always use this research.com ranking, actually rank mechanical aerospace together. So far, Northwestern has been ranked the number 6 in the world. And I believe this ranking is very much based on citations. And US News oftentimes is based on the rating or ranking of the department chairs. Oftentimes we feel the size helps. In our case, our size is much smaller than some of the high-ranked department. So I'm very proud of the department and working with a lot of talented faculty and the students. So the past year has been really exciting year that we actually start to work on 2 new engineering research center. One is the one that was awarded this year called HAND. So this is initiated by my robotics colleague at Colgate and Kevin Lynch. It is a center that looking at to build artificial hand, robotic hand in this case, to augment human ability. So these are AI-powered methods to empower or build very dexterous, means very light, compact, robotic hand system that can work on different tasks, for example, in manufacturing, in healthcare, as well as jobs that very dangerous to ask human to do. So this is the center about, is to build this robotic hand. And this is exciting thing because this is first, we call Northwestern lead ERC, and you can see some of the other collaborating institutions, usually the NSF ERC involving 10 years effort and involving at least 5, 6 different institutions. The one that I'm more involved that was mentioned early is called HAMMER ERC. So that stands for Hybrid Autonomous Manufacturing, moving from evolution to revolution. So one thing that's common of all this ERC is that you want to show an idea that can really change kind of the current industry. Okay, so the current manufacturing industry is viewed as like very human, artistic, like when you think about how you bend the sheet metal, you think about a lot of experience comes in, right? This human artism. But the new ERC is going to revolutionize the American industry by looking at autonomous manufacturing. And the one other very special thing about this hybrid is that we're not looking at just one manufacturing process. Something like a sheet metal used in like aerospace engineering, or even a structure like to repair like a catastrophic accident for human jaw. Those things could actually be made by a sequence of process, maybe starting with additive manufacturing, but followed by machining as well as sheet metal forming. So there's a decision to make in terms of what is the sequence. And there's a modeling you need to do, understand the material behavior from one process to another. So at Northwestern, Jen Chow is the whole ERC research lead, and I play the role of design thrust lead. And the main goal is to do concurrent material, product, and process design. Okay, so that's a very large scope. So today, in my talk today, I'm going to talk a little bit about what are the design methods we developed to enable that. But just a little bit background of my lab. My lab is called IDEAL, and it kind of really relates very well. The fundamental method we use is optimization. So when you do optimization, you want everything to be ideal, to be perfect, right? So in my early phase of my career, I've been working a lot under design under uncertainty. So that's the connection with Dr. Dimitri's like reliability-based design, robust design. And gradually, I get into an area that really I myself feel very interested in is how do we, looking at integrate data from both computer experiments and the simulations, how do we bring all these different people together when we try to use data to enable better decision making? So I have been developing a lot of algorithms to support that. So early phase of my career, algorithms now are integrated in some commercial codes. This is very similar to Professor Missour's work, like design under uncertainty, developing new computational methods. But the past decade, what I found a lot of fun is really using these methods, tailor them, and also extend them for design material systems. And those material systems can be microstructure at very lower scale level, like nanoscale level. It could be also metamaterial that focus on architecture design. There's a big difference between these two different kind of systems if you look at it. First, the manufacturing technique are totally different. Like metamaterial, you can actually use additive manufacturing to produce precisely the architecture. But material system, the method you use, like extrusion, mixing, polymer, those kind of methods will lead to very stochastic behavior of the materials. It look like they're like a random material system, but actually there's an important pattern behind it, okay? So one stochastic, one deterministic, and the methods to support them can be very different. So today, this is the topic I'm going to focus on today, is really show you a wide range of methods we're using or developing. But just first say a few words about why this topic is important. I'm showing some example here, like advanced material really refer to those systems that can achieve superior performance, and they have been used widely in energy, defense, even healthcare. In this case, it's a magnetic-driven robots goes into human body, like for cleaning. This is actually robotic called the endovascular surgery. So this is a programmable material system. And there's a lot of good impact, but if you look at this topic itself, it's not just engineering design. And I view this as we call interdisciplinary topic, because I've been collaborating with people in materials, in manufacturing, as well in mechanics very heavily during the past decade in order to show that we can really design something that achieves the performance that we want. So looking at the portfolio, I'm listing here some of the example of the system that we have been working on, and underlying this are a wide range of funding agent. And there's another reason I get into this field is this seems like there's growing funding put into this area from a wide range of like a funding agent. And also the uncertainty method really plays a big role that I will show you later on, that why uncertainty technique is useful here. But on the left is we call the design 2D material. So those are the things that can range from microelectronics, very like inorganic system, to soft material system like a polymer, composite, and in the middle can be like MOF, metal organic framework. These are very different material systems that I've worked on with colleagues from different disciplines, and they can also the focus, some of them are more at atomic scale level, some of them are more at a nanoscale level. But interestingly, the methods we're developing are generic enough that can be used for many of these different systems. And on the right is what we call design with material. I think most of us here are mechanical engineer. That's probably the domain we feel more comfortable with, right? And here we're using, oftentimes we're giving one material and we design the structure, right? It could be composite structure, it could be 2D, like a solar cell surface pattern. And here I'm showing some other metamaterial applications such as mechanical cloaking, energy absorption. So the focus here is the architecture design, the structure design. But these days, the two area, actually the boundary becomes more and more blurred, which means we're increasingly facing problem that need to integrate material design with structure design. And I think that's the future of the, this topic area is integrating the two. So why most of my colleagues, the people I work with, looking at we call a forward analysis from processing to structure to property then to performance. My group is more interested in the inverse problem. Given some desired performance, right? How do we quickly find out the solution for the material design in terms of the structure, composition, processing technique, and so on? And there's a difference between property and the performance. And the difference is here is that material scientists, they care more about property, right? And that is at a specific point, okay, location, what is the property? But performance always have geometry comes in. So geometrical design play important role on the performance at the end. And that's where mechanical engineer usually work with. So we, in addition to material design, and we also need to design the shape, topology, right, or size of a structure, which has important implication on its performance. Related to the slides I showed earlier is that material design itself, I think, is often confined or restricted by what manufacturing technique that we have. So in recent years with the HAMR ERC that I'm getting into a new paradigm called digital twin. This is a paradigm that create digital replicates of a physical system and use that to do decision making to guide the operation of a physical system. So manufacturing is a dynamic process, right? You have to tell what kind of laser power you use for additive manufacturing. But building a digital replicates is not the only interest in digital twin. What is important is this link between the physical and the digital system is to continuously using the information or data collected from the physical system to do we call the model predictive control. And that's using optimization and physics-based model. So this topic, I'm not going to go into details, but if you are interested in the paper, there's some of them already published on digital twin. So today, I'm going to talk mainly about structural, composition, geometrical design, and how do we combine them, not too much on manufacturing process design. But I want to use this turbine blades as an example to kind of show you the design research now, the challenge we face, or the interesting aspect is really design something we call the heterogeneous material system. So the turbine blades is a good example that you can say that at different location, like the bore, the ring, the blades, right? You actually like the material to be different. And you want the inner side could be fine grain, right, for strength fatigue. Also outer side, coarse grain for creep resistant. And then the blades, you're looking at a single crystal material for strength creep fatigue. And ideal system actually is not only 3 material. It could be continuously changing. We call this continuous material design. And I will show you some results later on. It's in a DARPA-sponsored project called the METAL. Exactly, it's the kind of system that we need to integrate material manufacturing capability, which is additive manufacturing, can deposit different material, even different composition of different alloy at different location, and try to achieve the best performance. And this is important not only from the performance point of view, but also from the cost point of view, right? Because if you, from the performance point of view, you will say, put the most important critical material everywhere, but that's very costly, right? So you want to use, we call the earth abundant material, rather than the real material, that cost material. So how do you do this distribution of material? That's a big optimization problem. And if we look at the soft material, you probably heard about soft robot, right? And they deform to certain desired shape. And this can be accomplished actually by controlling the strain at the different locations. Okay, so each location of the structure will have different desired strain, and this strain can be achieved by actually different structure design. So material design or achieving different property, you can do this by two means. First, you can change your material, right, to achieve different property. Second, you can change different structure. And that's the key idea of metamaterial, is to play with the architecture, and then you can achieve different property. In this case, it's an optical device that you don't see the human hand, right? It hides, and that is because surrounding this device, in this ring, it's a optimum design that put different property at different locations, okay? So in this case, it's optical related, that you can actually, with this structure, and when you have light comes in and goes out, and then you will not see anything in the middle. It's basically hide the object by controlling the property in the surrounding area. So this is a design problem. So we're looking at this kind of problem, and then, so what are the challenges, right? So this diagram really shows the people I have worked with in the past decade. Mechanics, material manufacturing, and the data science is in the middle that links all of us together. But in terms of the interesting design question, research question, the first question is the design representation question, is how do we describe this high-dimensional space? And whether we're using deterministic approach like this one, or using stochastic methods like this. And the answer is it highly depends on the manufacturing processing technique you're using. But there are some methods are much better than some others because they have smaller dimension, or we call reduced dimensionality representation. So in our research, we looked at how we reduce the dimension so we can handle the optimization more effectively. There's also a mixed variable problem, which is some of the variables are continuous, some of them are discrete, like what kind of filler we should use, what kind of matrix we use for the composite. All these are discrete choice. So you have a problem that you have to mix, you have this mixed situation that you have to optimize them together. And if you have done optimization or taken some optimization course before, you know that when you have a mixed variable problem, suddenly the search becomes very challenging. And you have to, historically people use genetic algorithm. And I will show you a method we developed that we think is more effective than genetic algorithm. And from the design evaluation point of view, we're increasingly facing problem that is very expensive in simulation because they involve multi-physics. Multimodal means some information come from experiments, some from simulation, and some from sensor. And uncertainty is always something very important for us to quantify and predict. We always have to assign, confidence interval or uncertainty prediction. And finally, is the challenge is in design synthesis. Synthesis means, given the requirement, how do we explore this space inversely? So synthesis analysis is usually forward. Synthesis is inverse. And how do we explore this vast design space? And oftentimes, it's multi-scale, nano, meso, macro. And how do we do co-design, meaning material, device, material, process, geometry. There's many co-design aspects, and the heterogeneity aspect I talk about. And finally, it is a resource allocation problem that you have to decide whether you want to expend more effort towards, say, collecting more data from computer simulation or collecting more data from physical experiments so that you can make more informed decision. So we view that as a part of the design. It's not just design artifact, but we're designing the process of data collection. That's something that I feel my group is doing some, take a unique aspect compared to many existing work only look at artifact design. We'll look at also the data collection. So data-driven design methods is basically integrate all this using statistical inference and also AI. And I purposely listed both of them here because statistical inference technique usually is to deal with small data problem. An AI method that some of you are very getting into learning more is normally to do with large data problem, right? So in the design material system, we think they're both are useful, but they all play some different role in the process of we call the closed loop discovery and design automation. So now this is I'm getting into the main part. I already spent 20 minutes, but I will quickly show you 3 different systems and some different methods behind. One is starting with nanocomposite, focus on morphological design and also choice of composition, processing synthesis method, goes into metamaterial that focus on architecture. And then the most recent work we're getting into is programmable material system that are responsive to the external stimuli. So there we call intelligent material system that can react to a different stimuli such as light, temperature, and then can accomplish multifunctional behavior. So we call some people call this multifunctional material system. So step by step, the nanocomposite system is really a problem that I'm giving you an example here is called the nanodielectric. It's already finished the DIMRIF project that working on with both people are doing modeling and experiments. So the design decision is the composition. In composite case, it's what kind of polymer, like either PS or PMMA. And the synthesis method here includes a surface modification technique. So we have 3 different types of technique we're considering. And the morphology here shows that the microstructure, this is an image, 2D image of microstructure. You can see that some of the structure is very sparse and some of them are very dense, right? And all this have a huge impact on the mechanical behavior. So we're using both finite element and the physical data collection, and using a method that I will introduce you next is called the mixed variable Gaussian process combined with Bayesian optimization. We found that this method is very helpful, useful for small data problem. So this is what I call the statistical inference method. You start with some data collection and you use a Gaussian process to build a machine learning model. And this machine learning model has the capability to tell you the uncertainty at the location where you don't have the data. You can see that you have 4 data points if assuming single variable, and there are infinite ways the curve can pass these 4 data points, green, red, blue, right? But this method, Gaussian process, use a correlation function. It can tell you at the location you don't have the data. So it's based on the distance between the data as well as the behavior to tell you how much is the uncertainty. So with that information, we could now decide how do we pick the next data points. And this is done by something called acquisition function in Bayesian optimization. It makes a trade-off between explore more in the space, which is reduce the uncertainty, versus try to optimize the behavior based on the current function. So here we're doing minimization, let's say. So you can say that this point is the optimal result, right? But on the other hand, because the model is still in the early phase, there's a question maybe somewhere here has huge uncertainty, the behavior can be even better than what you currently have, right? So it's a trade-off between exploration and exploitation. So that's called the acquisition function. That's the key idea in Bayesian optimization. So you pick a next point by maximizing this acquisition function, and you add it to this data pool, continuously update this model, and at the end, you will find the so-called global optimal solution. And the global solution can handle very highly nonlinear behavior. So our extension of this method is that this method has been primarily used for called continuous behavior. It cannot deal with inputs that are qualitative. Okay, so here we are introducing a new set of variable called the t. So x is continuous, and the t is the category variable. And I'm giving an example here. The category variable, say, can be the shape, okay, of the structure. It could have 3 different possibilities there. And using instead of using physical descriptor that we don't have a good idea what's the underlying descriptor to describe the behavior, we actually create a latent space, which artificial sets of continuous variable. And this case, identifying the location of this different level in this space becomes additional variable when we try to do the maximization of the maximum likelihood of function. So conventionally, when you only have the continuous variable, you identify the variance, covariance, and the roughness parameter. Here we're introducing z, the latent variable. So in this case, 2 coordinates, meaning each 3 level means 6 latent variable we have to add to this curve fitting or optimizing the likelihood of function. And once this location identified, it's a supervised learning. It has a physical meaning that when the 2 levels are very close to each other, it means their impact on the response of interest. Y here can be the property that you're interested in. The correlation is very similar, or the impact is very similar. And when the level is very far from, like triangle is very far from this shape, it means that its impact on property is very different. So this is, we call it interpretability or explainability of this machine learning technique. It gives us some insights in terms of different level. So this code actually has been used on a wide range of problems that there's a lot of downloads. It's not only used for material problem, but we published a paper 4 years ago on how we use this for material design that has both qualitative and quantitative variables. So for this nanodielectric material design, before we do optimization, we also have to handle this high dimensional, the morphology. So we're actually using a transformation technique called spectral density function to transfer this structure, very complex structure, to the Fourier spectral domain. In this case, it becomes a step function. And now we only need 2 variables, the lower bound and the upper bound. So it's a huge dimension reduction. And for the nanodielectric material, what we did is that my collaborator, Linda Schadler, her lab actually produced many of this material using different processing conditions. And we did image analysis. And later on, we found that this shape of spectral density function with 2 variables, one is the dispersion parameter, another one is the a coefficient, together with volume fraction, they are sufficient to represent different type of microstructural morphology. So for morphology design, we only need 2 variables in this case, the theta as well as the volume fraction, and these are the continuous variable. So using the GP method as well as the Bayesian optimization, here what you're showing is the process that how the data are picked. So initially we start with some data points that are randomly selected. We call them randomly initial design. And after that, using this acquisition function, it starts to pick points. And what is interesting of the contribution of our work is that you can see that we can deal with disjoint design space now, because we have this smooth function called LVGP, latent variable method, can link the 2 disjoint space. And in this case, the joint space are related to the different kind of polymer. Like on this upper corner is all PMMA, and this lower corner all PS. The surface treatment method actually are spread around. So this is the Pareto frontier that look at 3 different criteria that's interested in. And the green points, the star points, are we call the Pareto frontier. At the end, these are the good design that you can choose, and it shows different kind of morphology that you have. So you can imagine that this could be a method that can guide either purely physical, experimental-based process, or simulation together, simulation only, or simulation with experiments. In our case, we actually have both simulation experiments, and we are exploring different kind of morphology and different kind of polymer choice. And we found that we compared to genetic algorithm. You can see this is our approach with using Bayesian optimization. It is statistical because depending on the initial design is random, right? Initially we pick like 30 sample points. So you could have lead to different process. So we did try many different repeated, different starting sample and look at the statistical behavior. And on the right is genetic algorithm, which also randomly explore the space. You can see that the Bayesian optimization is much more robust compared to the genetic algorithm. And the LVGP really allow us to put qualitative variable together with quantitative variable and with a single GP model underlying it. And recently, we're extending this method to multi-fidelity modeling by assigning the fidelity as a category variable. So the data source or the low fidelity, high fidelity can be viewed as different levels. And now it can start to explore collecting data from different source and the different fidelity of model. So that's a interesting extension. So I talked about the nano composite, which is a very stochastic, stochastic system. Now I switching the gear a little bit to talk about if the material is already designed, how do we design the architecture? So here the case is really the high dimensionality, because if you think about structure design, right? If you think about find an element, each element there's a choice of either 0 or 1 or something else. So this is the area we found that the machine learning technique are very useful. The high end, like a generative modeling, CNN, those techniques are become very useful. First, metamaterial system, it's an interesting kind of system that you probably heard about the negative Poisson ratio, right? Structure that you can achieve negative Poisson ratio. And this kind of system also have very good energy absorption behavior. And it could be used in orthostatic structure for stent surgery that have both, it's like a spring structure, right? Very strong, at the same time, it can easily flexibly diffract to different shapes. In optical area, there's optical metamaterial, acoustic metamaterial. This is something using in civil engineering. You could actually, this is futuristic. We haven't seen that yet. Is you can design the concrete highway into this kind of structure. This is amplified that actually could take the vibration of a car, right, and convert it to energy. So it's an energy harvesting, kind of a structure. So there's a lot of things you can play with architecture to achieve different functionality. So the challenge here is really the heterogeneity we want to consider. So I'd like you to imagine that the problem is like a design a butterfly. First, we have to design the overall topology of this butterfly, the shape, right, the wing shape. And the secondary, we think that each location of the butterfly, it should have different structure, that it can achieve a distribution of the ideal distribution of the property to achieve certain function, okay? So if you do use topology optimization, you know that I show you a picture here. It's a conventional topology technique. It starts with a block. Using optimization gradually converge to a structure. In this case, it's a kind of a test problem people use to show how do you reduce the weight of a beam, right? If you apply a load, it have the best compliance, kind of structure. So most of the existing topology optimization methods are only suitable for a material that's fixed, okay? So we want to design heterogeneous structure. So how do we do it? We actually come up with a data-driven method that we build a library of different unit cells. Okay, so different kind of unit cell could be lattice structure, it could be isosurfaces, it could be some other, there's different way you can generate structure. There's infinite amount of way. But the machine learning here is input is the structure, the output is property. So here is example mechanical property. That is basically a matrix we call the constitutive law, right? It has C11, C22. So it's multi-element. It's very high dimensional in terms of the output. And this machine learning will tell us the behavior. And what is interesting is that when we do the data acquisition, in the design space, the manifold do not have any overlap. They're very different. They're at different locations. But in the property space, actually, there are lots of overlap. It means that specify the target property can be achieved by many different kinds of architecture. But the harder problem is really superior property, right? How do we achieve that? Are we able to design a structure that we never seen before that can achieve superior property? So the research question here is how we unify this space when we have multi-class unit cell structure, and how do we go beyond the existing property data set and go for the the really higher end property. So my student, Dokso, now he's a postdoc in my lab. His work on called the task-aware data acquisition actually won the best paper award in the IDTC. And the idea is to use methods to guide the data collection. So in this case, the geometry shape is free. It's already there that we actually collected like close to 100K different geometry. But what is the intelligence here is simulation will take time to simulate the property. And here we call the anisotropic behavior, okay? That behavior that closer to the two ends. And if you do only random simulation, just randomly pick those data set, what you will get is a distribution. It's like a normal distribution of the property. But what we want is this interesting property at the extreme ends. So he applied two different techniques. One is only consider diversity. And diversity is measured by shape diversity as well as property diversity. Actually, it's very interesting measurements in terms of improving the diversity of the data set. And this is what you get. Okay, so now you see it's more uniformly distributed. But using active learning, which combine diversity and as well as the quality, now you see that the data has two peaks, which means they're now pulling towards, so the blue points are the sample that is picked using our algorithm. So it kind of continuously retrieve data from a library, do simulation, and then forcing those things going into the envelope. So the envelope is the theoretical bound. You cannot go beyond the theoretical bound, right? But the data-driven method, if you blindly pick data, you may end up with something never ideal. But using a task-aware method, you can force the data goes into the desirable region. Once you have the data, then you can do machine learning. So in this paper, it's kind of hidden here a little bit. It's published in Advanced Material last year with 3 of my students working together that we looked at 300 paper, start to use machine learning in this field and inverse design. So from the physics point of view, they can be put into like optical, mechanical, acoustic, thermal, and the machine learning model, you see some of the things you're familiar, deep generated model, multi-layer perception. So this is a nice diagram to show what work like falls into which category, right? So you can see a lot of the work using deep generated model, some of them using Gaussian process. And what is interesting is the optimization scheme. There are also 2 different categories. One is called iteration-free inverse design. It means that once you train the machine learning model, given the targets in the property space, it can tell you directly what is the optimal geometry without any additional simulation. So this machine learning model goes 2 ways, forward and backward. Iterative design is another technique that you train the machine learning model, but you still need to add a optimization solver on top of that. And then you solve it, but now it's a cheaper model. It's optimal, it's already a surrogate model. So you can see here, there's a distribution of methods. It's very interesting to look at different methods that have been explored. But unit cell design is not our goal. Our design goal is the heterogeneous material structure, right? That could be different at different locations. So we developed 2 strategies. One is called bottom up, another is called top down. And both strategies combine machine learning with the conventional topology optimization. So here at each location that we rely on a machine learning model that is created using the data set I talked about, and now it becomes a surrogate model that surrogates the constitutive law at each location. And upper scale level, we still used the conventional topology optimization technique to do the optimization. So you can see this is the structure, like the door knob. It's a compliant mechanism design. So start with this geometry, and we can decide 2 different material, soft and hard material, and each of them have 8 different architecture you can choose from. And this is the optimal design that has the best displacement. So output is maximize the displacement. When you turn the door knob, you apply force, right? You want to achieve the biggest displacement. So this is the purely using this database, okay? And that's a machine learning model that we can and then topology optimization, we can design this optimal distribution. So what is the model behind it? The machine learning model actually start with very different concept of the unit cell. We make sure they are all connected in this case. And also varying the different thickness, so that's the weight, right? And with this LVGP, here we again use the latent variable Gaussian process model I talked about early by treating the class as a category variable, qualitative variable. In the latent space, we can actually see what are the concepts that are similar in terms of their property, and what are the concepts that are different. Like we have the very similar observation in both the 2D and the 3D kind of structure. So this gives us some insight. But what is interesting at the end is that you can see that the method can allow us to design heterogeneous system. What if you say, I don't want to be confined to the existing data set, right? I want to design something very arbitrary and free form. And that's where the generative modeling is useful. Generative modeling used like in ChatGPT these days, right? So how do we use it for unit cell, like analyzing the data set we have? We create a data set that some of them belong to truss type and some of them belong to isosurfaces. And then we create this generative model, and now it can create very novel design, even though you may argue they are interpolation of this different class right there, but they're still very original design, and they can still achieve very optimal property because they are interpolation in the geometry space, but they're not necessarily interpolation in the property space, right? The property can still go beyond. So with this data set, we actually designed this is acoustic metamaterial that achieve, we call the multi-class functionally graded structure, okay? That you can achieve gradual transition of the property from one location to another. So generative modeling could be quite useful in creating new designs in this case. Top-down approach look at the problem differently. It starts with topology optimization and determine what is the optimum property at each location, and then retrieve the library and say which design or architecture is the best. So here there are two sets of variable. One represents the property, one represents whether we will have material with or without material. So 0-1 decision like we traditionally do in topology optimization, and plus that the property is a design variable at each location. So this is done also by topology optimization technique. What you're seeing here is the evolution of how the C11, C22, C33, the property converged to different value. And then we retrieved library, and we formed, this is the final architecture, tested, it's a collaboration with Cartech. The paper is published at PNS to show that this is a mechanical cloaking structure that when you hide objects, you can imagine that you hide the different objects in the middle, and you can design the architecture like the packing structure surrounding it, and when you apply the load, the displacement is the same as without the object. So you can see that this displacement and this displacement are very close. So in this way, you don't feel there's an object in the middle when you apply the load. So we call this a mechanical cloaking device. So this is a good example to show top-down approach. The bottom approach, I want to also show you another example. This is very new results. We're still writing paper. This is going back to the turbine blades I talked about early. DARPA Metals project. Our team is a collaboration with GE, General Electric, we call it RADICAL, Rapid Array Dimple-based co-design gradient material and the geometry. So the end goal is to design material for these turbine blades that we call continuing material design, means at each location, the composition can be different. In our case, we consider 4 different alloy. So this is a project that actually the experimental research is more than half of the budget. Okay, the computational research is a small amount of it. So my colleagues and also GE colleagues work together to design what we call the high throughput experiments that can test the material composition under different temperature. Okay, so each of this location has this gradual gradient change of the material composition. And how you make it is actually using additive manufacturing. And then testing, and we build a material model based on those data then feed to topology optimization that consider both thermal mechanical coupling. One challenge in topology design is the gradient information that you need. And especially when we deal with highly nonlinear behavior like a creep behavior, okay? And here we're using something called the JAX FEM. It's called differentiable simulation it's a language actually. You can allow you to program differentiable simulation that can allow you to do automatic differentiation. This is something I see also a trend for the future in terms of integrating material design with structure design. So here, with this differentiable simulation, we can calculate a gradient very quickly for nonlinear behavior, and we can design continuing material. The objective here is the cost associated with criticality. Criticality is about whether this Earth abundant or Earth real material. Okay, so we assign different costs associated with that. This in the middle is the optimal graded material design. Here we're only showing two materials, Inconel and the stainless steel. There you can see that different location, the material composition is different. And compared to single material using either one or the two, or homogeneous material that is the same everywhere but have different composition, you can find that the graded material is the best in terms of the cost as well as factor of safety here is related to displacement. So it has this coupled thermal and mechanical analysis that we already seen the result, a very promising result. And DARPA really wants to accelerate the speed for both experiments as well as optimization. So for optimization, they told us like less than 12 hours that you will get a design, like giving you any geometry, okay, a turbine blades, you have to come up with optimal solution. For the nonlinear problem right now, or for the linear problem, it only takes 2 hours currently. So we're working on nonlinear problem, like having creep behavior and those, much more difficult behavior using the differentiable technique. The last topic is programmable material that I will go really, really quick now. And this is a really exciting area that we call the intelligent material system. So here, in addition to composition and architecture, we need to design the stimuli, which could be programmed, and we also need to design the material system. So we call it the programmable material. This is my NSF-sponsored called the Bright Fellow Project. So it's a single PI project, but I'm working with some younger faculty who are really have the technology of fabricate this kind of called 4D printing. Like you can build the stimuli into the system. And most of this system right now are soft material, combination of soft material and hard material. We call it programmable because at each location it's like coding, and you can decide what material you want to put and correspondingly what process condition you have to use. There's actually a strong coupling of processing condition with the material behavior. So we already get some interesting results. The challenge point of view, the design challenge is really this large design space. Stimuli, each location, material, each location, and then the architecture. So how do we couple them together? That's really something that we have to handle. So several things we are looking at. One is the magnetic soft material system that I worked with Renee Zhao at Stanford University. So this kind of system that you can see that it kind of responds to the magnetic field. So this is example like in the by Professor Xuanhe Zhao at MIT. This is a picture from him. You can use this for surgery, right? You can control the external magnetic field, control how this Y is going to travel through the human body. So this kind of system has to really respond and actuate. Actuation is a big problem. Like it had to, in this case, the externally controlled system had the energy that's sufficiently enough to create the actuation that you want. So here's an example. This is already the results published in Nature Communication to show you we call the shape morphing using called the kirigami. So the kirigami design, what you want to achieve is start with the same geometry like a block. You need to decide where you cut your material. So each of this cutting point is a design variable. And each element, where is the direction of the magnetation, is also a design variable. So it's a very high dimensional problem and involving multiple physics. So the physical validation here, you can see that this is from Renee's group, her group at Stanford, they print this structure. These elements have different direction of magnetation, and it responded to the external magnetic field, which is showing here. And then the lower part shows that they can actually achieve multiple state from closing to opening. That's another challenge. Like it's not just a single direction, it's multiple direction. Another one is optical. In optical area, I know that this department is very strong in fluid mechanics, turbulence. I think this method has been heavily studied in those areas. It's called neural operator approach for machine learning. So we're using this for designing optical metamateria. Here, the functionality is that you have a geometry, and when you manipulate the phase field, and you want it to generate targeted signal in the focused area, okay? Either one point or multiple points. In the past, we used traditional optimization technique like Bayesian optimization. We were never able to catch what is the optimal geometry. Now here, the geometry could be different. Here we're designing same geometry repeated, okay? So the design space is both the phase field you're applying as well as this geometry. So very large dimensional space, and the optimal performance is targeted location of concentration of the signal. So now we're using the neural operator, which model input are a field. So the field could be this phase field as well as the geometry, and the output is also a field. So this machine learning model allows to specify any targeted behavior. So I'm showing some example. The training data set is about 400 different shapes, 36 different phase diagram. Okay, so combine them together. And this data set are used to train. Now we can do concurrent design. And for any targeted, like either here or two targeted location or one, that we can accomplish different design, optimal design. The last example I want to show is a soft material system that using liquid LCE structure. So this is a technique my colleague Ryan Chuby is able to produce to do 3D fabrication. A nice thing about LCE that is compared to shape memory alloy, this system has much better like a strain behavior, very high strain, high deformation. So what you're showing here is a reversible system, and the reversibility is very important in the programmable material system. Like when you released the signal, you want to go back to the original, right? So liquid crystal elastomer is very good in doing that. So you can see this is a design, this is already optimal solution that with different structure, we can change the circular shape to a ellipsoid, like an egg. Okay, so a ball becomes a egg shape using optimal design. And you may notice that at different location, the thickness are different. And this is purposely designed because you want the edge, right, to be stronger. And this is controlled by changing the processing condition. So it's a concurrent process and the structure design problem. Again, we use a machine learning model that I'm not going to go into all the details to build using data to build like a behavior of the model as a function of all this processing condition, and using topology optimization that we can design the node location as well as what kind of stimuli you should use. We could actually handle multiple stimuli right now. And what is interesting with multiple stimuli is now we can design something. I'm going to skip through this, different speed, pressure, cross-section, each location is different. And you can see that it can go through the morphing process. But the future is thinking of this kind of system is what people call soft robots, right? The soft robotic system is the one that can respond to this different actuation to build what we call muscle, right? So what is the human muscle is accomplished by putting different material at a different location that have different strain behavior. Okay, so if you're in a soft robotic system, you also want different material at different location. They have different strain behavior that can react to the external stimuli. In this case, we're showing both light as well as temperature. And you can, in this case, one single design two different stimuli lead to different deformed shape at the end. So that can be, if you give me any shape you want, that I can inversely infer, what is the structure you can begin with. So I'm already exceeding the time, and just want to summarize here, like in my research, we kind of also evolved, right, from material design to architecture design, now to programmable material design. And we have tried many different machine learning techniques. There are small data problem methods, there's a large data methods. At the end, we are getting into this domain that we have to also consider dynamic behavior, which is beyond the conventional static structure design, that we have to use method like differentiable simulation in order to get the gradient information we need and dynamic behavior that we want to model. So thank you very much for listening.
We're running out of time, but let's have one question, and then I will invite you to join us to the reception, and you can keep talking to Dr. Chen. Mm-hmm. Any question maybe on Zoom?
Yeah, of course.
Okay. Yeah.
So, very nice talk, man. You talked about SDF, right?
Yes.
Which seems to me, because you said Fourier, it seems to me you need to have periodicity for the material to apply, right?
So in our case is SDF. Right now we're applying to something we call isotropic material system. Yeah, but you actually can have higher order spectral density function for an anisotropic system. So we did both anisotropic, isotropic, but the anisotropic you need to introduce some additional variable to do it.
I was wondering if you could use different polynomials to do anisotropic or non-periodic, right? The polynomials like, I don't know, like Chebyshev, genre, everything.
Actually, these are not a polynomial. These are more like some of the typical model we have is more like Gaussian process model. There's one, go back to the function that I showed, it's actually exponential function. But the transformation here, what's going on, people in optical area actually have been using this a lot already. They're doing spectral density function representation. Like the Blu-ray, you probably heard about Blu-ray, is very complex, like in this disk, right? But actually, after you do the transformation, it's only a few variables. So this kind of transformation is a Fourier spectrum domain. And Fourier function is, so there's transformation. But at the end, there's only, for many of the functions, there's only 2 to 5 variable will be sufficient to do the curve fitting. So in this case, it's just exponential function that you can see that for this one and this one, there's only volume fraction is important and this parameter is important to identify underlying curve. So we found it's interesting that there's only several, up to 5 different kind of curve. There's actually in the literature, like gamma curve, Gaussian model, that will be sufficient to describe many different kinds of material system. But they have to be something like this. It's like particle based, but it could be free form. It doesn't have to have this shape, like a round shape, not necessary. Could be free form. But this method is not going to work for, say, this morning I talked to one of the colleagues here about ceramics, defects, those that doesn't have periodicity. It becomes very difficult. So this, we assume there's a periodicity that from one region to another region, this pattern repeats.
Yeah, that's what I was trying to say. That if you use other basis functions that are not periodic, like sine and cosine, you might be able to extend this to general case.
General case, yeah, you're right. There's some cases that we looked at those, and with some extensions, Thank you.
All right, let's thank Dr. Chen for a wonderful talk.
Yeah, thanks.